can remember that I record everything. And you can go on YouTube and you can listen to it. And yeah, it's not the most fun thing to do at night. I don't care if it's not fun. If you want a mark that's better than what you got, that's one way to do it. Okay, so most of the forces we're familiar with in everyday life might be called contact forces. This is basically what I talked about yesterday in a condensed format. So for those of you that were away, or for those of you that were zoned out, listen carefully. Contact is required between whatever it is that produces the force and whatever it is that receives the force, as when someone pushes or exerts a force on a lawnmower. An electric force, however, is one that acts at a distance. Remember that concept from yesterday? Okay, so it's an electric force, it's acting at a distance, no contact. That is, they act even when the bodies involved are not touching. This idea of a force acting at a distance is sometimes difficult to understand, so the concept of a field was developed to explain how these forces operate. And I talked about that yesterday, but how this force field is our model of explaining how this works. We can visualize an electric charge giving rise to an electric field that extends out from the charge, permeates space. The diagram at the left shows the electric field coming out from the positive charge, Q1 in all directions. We tend to use the letter Q for charges. A second charge, Q2, would experience a force in Q1 because of the electric field. What is the direction of this electric field? Outward or inward? Outward. And you'll notice that the charge on the big Q1 is positive, and positive things have charges that go out. An electric field is detected with a positive test charge. We looked at that yesterday. This elementary positive test charge is placed close to the charged body whose electric field we want to determine. The magnitude and the direction of electric force acting on the positive test charge is the electric field. Why do we use a positive test charge? No reason at all. We just all decided, hey, let's use positive. Could we have decided let's all use negative? Sure, we just chose positive. Interesting note, Ben Franklin a lot of people think that Ben Franklin got it wrong. He was the guy that came up with that positive and negative thing. And when electricians talk about current, and when physicists talk about current, it's just two different things. Current goes from positive to negative, which is not the case at all. Electricity is the flow of electrons, which is a negative charge. So when electricians talk about current, the physicists talk about electron flow, they're opposite directions. Franklin kind of sort of got it backwards, just by fluke, 50-50. Paragraph underneath there. It's important at this point to remember that all forces are vectors and must have a direction associated with them whenever a calculation or description involving a force takes place. So back to our old friends, vectors. Have we had a unit yet where we haven't had vectors? No. Since the field is a special case involving a force, then it too must be described as a vector. Note that the electric field is directed away from the positively charged point. I keep repeating that. As the positive test charge moves closer to the positive charge point, the electric field becomes larger or stronger, just like the gravitational field. Note that the electric field points towards a negatively charged object. We're going to do more of that tomorrow. In any case, the electric field is described as the electric force acting on a single positive test charge. Put a star, highlight that one right there. That basically is the definition of an electric field. If you can't find it, it's because you haven't been following along. If you haven't been following along, you should be. Because that's what good students do. That's what helps you understand what's going on. This equation can be used to determine the electric field when there are two charged objects. That equation in the box right there is the one we're going to look at today. E equals Fe over Q, where E is the electric field, and it's either measured in newtons per Elch, and I'll explain what Elches are shortly, or newtons per C, N per C, newtons per Coulomb. Fe is the electric force on the charged points. What do we measure the electric force in? Newtons, it's a force. So it's force electric. Q, small q, is the electric charge in the charge point where the electric field is to be determined in Elch coulombs. Little footnote, little side column point here. Little q is usually used for small charges that get pushed around. Big Q is used for big charges that create electric fields. That's the difference. Little q is the ones that get pushed around. Big Q is the one that creates the field. Okay, on the next page here, you're going to write that up in the notes, so I'm just going to ignore it. That was kind of yesterday's review. I'm going to put it back in my binder so it doesn't get lost. I'm going to use the rings. You can put yours in your binder now too. Okay. As always, you write down what you need to write down. You decide what's important. I'll give you some cues. These are more notes for my little speech, which I've already been really through a couple times. So electric field is similar to a gravitational field. Gravitational field is defined as the amount of force exerted upon a unit mass. We defined that in the last unit. The gravitational field is the amount of force exerted upon a unit mass. On Earth, it is 9.8 newtons per kilogram. For every kilogram of mass that I have, the scale shows 9.8 newtons. Let's see if I remember what I was before down. 850? Say 850, it'll make it feel better. Yeah. So, on Earth, 9.8 newtons per kilogram. Now, is that constant, more or less, around Earth? It is, right? And that's because the mass of the Earth is, for all intents and purposes, constant. Or is it? Is the mass of the Earth constant? How much stuff we have here on Earth? Like, I mean, 20-some years ago, Andrew wasn't around. He's a good 75 kilos. Where did his 75 kilos come from? Conservation matter. Is the mass of the Earth constant? What about all that gas we're pulling out of the ground? All that oil, we're burning it up. It's just in the atmosphere now, right? You got dinosaur molecules in you, don't you? We all do. Is the mass of the Earth constant? More or less, yes, if you don't worry about all the things that we've sent out into space, right? Okay. So anyways, what I was getting at here was that the mass of the Earth is constant, which makes that 9.8 constant. But are the charges of objects constant? Are the electric charges of objects constant? No, they're not. So electric fields are different. That's one other way that they are different, is that they differ dependent upon the charge. Okay, so I'm sort of showing you the similarities between gravitational fields here and electric fields. While a gravitational field exists on any object with mass, large masses such as planets have strong gravitational fields. I think you know that already. Right? I'm just sort of showing you the similarities again between gravitational fields and electric fields and the differences. Around any charged object, there exists an electric field. Is there an electric field existing around my box of pencils? No. How come? Not charged. It was free. Is there a gravitational field around my box of pencils? Yes, it has a very tiny bit of mass. It has a gravitational field, so small that it's negative. But around a charged object, there exists an electric field. Objects with a large charge have a strong electric field. Those fields are shown by a series of arrows radiating inwards or outwards, and these are called lines of force or field lines. Do these field lines look like vectors? Do they look like them? Yeah. They look like them. Are they vectors, Brody? They are not. Okay? I wish they could come up with a way to distinguish between the two of them, but I haven't seen one yet. Okay? So they are not vectors. In other words, the length of them doesn't matter. The length of these field lines actually goes how long? Literally forever, right? There's an example. You can draw it if you want. Do you have to have the exact same number of lines? No, it's just a visual. What do you think that +1 in the middle means? Positive charge, maybe 1 coulomb of charge, 1 megacoulomb, who knows, kilocoulomb, right? The key here is that the arrows go out. And once again, the closer the lines are, the stronger the field is. The strength is dependent upon the distance, and it is an inverse square law again. Strong. Weak. There was a question on the test about inverse square law. Many of you got it wrong. So that tells me I better redo it here. Inverse square law. You'll get them soon once everyone's done. If I'm twice as far, let's talk gravitational. I'll use Dan, who's close here, if you don't mind. Okay? Dan and I are about 1 meter apart. There's X amount of gravitational force between us. We're now 2 meters apart. Is it half X, a quarter X, 2 times X, or 4 times X? Inverse square, 1/4. I'm farther away, I'm twice as far. 1/2 squared, 1/4. If I'm 3 times as far, it's now 1/9, 3 squared. If I'm 4 times as far, it's now 1/16, 4 squared. Inverse square law. If I get closer, right, if I'm here, 2 meters, and it's X, and then I go here, and I get twice as close, it's now 4 times stronger. Inverse square. Maybe I didn't do a very good job of that. If the distance is doubled, the field strength is 1/4. That is true for gravity, it is true for electric fields, it is true for light intensity, it is true for sound intensity, anything that basically goes out in sort of that 3-dimensional. Right? You only have to get a little bit farther away from the big giant speakers for it to be a little bit quieter. Quite a bit quieter. Same thing with light. It's known as the inverse square law. To show the direction of the field, bring in another smaller charge, a small positive test charge. In this case, it will be repelled. It'll be pushed away. Come on, where's the picture? Right? If this is positive, big giant positive, capital Q, if it's positive, our small positive test charge will get repelled, and the lines go out. Okay? So, unlike gravitational fields, electric fields can push or pull. And you saw these pictures yesterday, right? It was on that page. Do what you need to do to get it learned. Is the force, I'm going to wait a second. Is the force on this small positive test charge going to be constant? That was a quick answer. No, Brody? How come? Exactly. What we just talked about. The farther it gets away, the field strength gets less. Does the amount of the charge on this guy change? No. Does the amount of charge on this guy doesn't change? But that doesn't matter, right? The electric field strength changes, so that means absolutely the force gets smaller. What's that going to do to the acceleration of it? Make it weaker, slower. So it's going to actually, when it's in here close, it's going to be accelerating really fast, speeding up. Is it still going to be speeding up? Yeah, just not as fast. There's still people that are having trouble with what acceleration is. I can sense it. Objects with a positive charge that fields a point away. If you don't know that at the end of this 2-week period, we're in trouble. Remember I said, if you mess up this positive test charge on all those questions, every single one's going to be wrong. So get it right. If we were to have a large negatively charged object, what would happen to this positive test charge? It would be attracted. And the arrows go which way now? Inward. Toward. Q1 is negative. Objects with a negative charge have fields that point toward them. Same question. Easy answer now. You know it. Does the force on the positive test charge stay the same? No. In fact, as you get closer, that force gets bigger, and the acceleration actually does what? Increases. The acceleration increases, not just the velocity. the rate at which it's speeding up is going to get bigger. I'll try to speed up and I'll try to stay off tangent or on topic. The amount of attraction or repulsion can be used to indicate how strong the electric field is. In fact, Millikan used this idea. And the field strength is defined as the force the field exerts on a unit of charge. In gravitational terms, it's the force per unit of mass, kilogram, and on Earth it's 9.8. But electric fields are different, they vary, so the field strength is defined as the force the field exerts on a unit of charge, usually a coulomb, or an elementary or fundamental charge. And what is this elementary charge? It's the one that Millikan came up with. 1.6 times 10 to the minus 19. A number that I will forever remember. Because I've said it so many times. I should contact former students and see if they remember. That'll be fun, eh? Hey, how's it going? Remember what the Millikan charge was? Just Google it. They might, yeah. Hey, how's it going? I haven't talked to you in 20 years, but do you remember what the Millikan charge was? Because I forget, yeah. Okay, so the formula we're going to use is pretty straightforward. It's one of those magic triangle formulas. E equals F over Q. The electric field strength is the force per unit of charge, F over Q. E equals F over Q. Where E is the field intensity or strength, measured in newtons per coulomb. Fe is the force measured in newtons, and Q is the charge in coulombs. Generally, we measure it in coulombs. Should we do a sample question? Should I show you how to do these problems? Brendan, should I show you some problems, some samples? Doesn't matter what you say, I'm going to do it. Oh, now this is actually important. I'm glad this came up here. Because some people get this wrong. Put a star beside this one. The intensity or strength of electric field is the same for a positive charge as it is for a negative charge. Only the direction is different. So what I mean there is a positive 10 coulombs and a minus 10 coulombs have the same field strength. It's only the direction that matters. Positives are not stronger than negatives. North poles are not stronger than south poles. Only in direction. Is it being repelled or is it being attracted? It kind of depends on how you set it up, but generally, yes, positive would be the way, right? So a lot of these little directional things are you get to define. I mean, there's conventions, but yeah, good question. There are questions coming up where objects are falling and electric charges are up, kind of thing. Forces are up, and so down is negative because of gravity. So, yeah, good question. Okay, so make sure you get that. Positive and negatives, same field strength. It's only the direction that differs. Okay, I only got like 3 slides left here, right? Here is the example that tells you how to do these problems. And then I'm going to give you time to work. What is the electric field intensity at a point where a positive charge experiences a 3.2 Newton force? Have we talked about scientific notation yet on calculators? Have we done that? I always forget where I'm supposed to. Don't think so? Okay, so we got to spend a few minutes talking about scientific notation on your calculator. You all have it, you probably just don't know how to use it. Or you've been taught it incorrectly, actually. With all due respect to your teachers that before you. I'm going to show you the proper way, or what, well, I guess I should say, what I think is the proper way. Maybe I'm wrong. And I'll certainly stand corrected if I am. What's the unit for what? Field strength, newtons per coulomb. Okay, so example number 1, I probably have it right here. Come on. Here we go. So we're going to write the formula like we always do. The force, how can you tell the force? It says 3.2 Newton force. 3.2 newtons here. The positive charge is 2.4 times 10 to the minus 6. So there it is right there. And when you divide it, 3.2 divided by 2.4 times 10 to the minus 6, you get 1.3 times 10 to the 6 newtons per coulomb. Now, I absolutely insist that you show me you can do that on your calculator. You want to practice this. Get out a calculator and try it. You should have one of 3 buttons on your calculator. Can I just show this one? So if you've got this one here, which is, I think Walmart has, right? I think I've seen these Costco. Okay, so I've seen more and more of this calculator. I'm a bit of a nerd. I've seen every type of calculator there is out there. Okay? These ones here have times 10 to the, is that a Y? Or is it an X? It's kind of up. These ones have times 10 to the X. Other calculators have an EXP button. Who has EXP? Okay, EXP means times 10 to the power of. Do not use times 10. Use the EXP button. Some of you will have EE. Look and see if you have EE. It's quite often a second function button. Okay? EXP or EE are the same thing. Do not, I say this 3 times, do not, and yet there's still at least 5 people that are going to do it. Do not go times 10. Do not do that. Use EXP, or if you have the times 10 to the X button, or if you have the EE button. Okay? You know, I get the right answer? What I normally do at this point is I wander around and help people individually. So if you feel you're good, you're ready to roll, go ahead and start the problems. Okay, I'm going to do a second sample question right away. I'm going to get to everyone to see if they know how to use their own calculator. This 0.02 would be 2 times 10 to the 1, 2, minus 2. I'll take both those answers. Usually, my sort of convention is, if it's more than 2 or 3 zeros, you go to sign notation. Nobody wants to count. Is that 3 or 4, right? Nobody wants to count. So if it's more than about 2 or 3 decimal places, put it sign notation. Okay? I'll have both answers on my paper. It's not a big deal. What I don't want is 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 0.00002. Put that sign in low. I ain't counting them. Okay. Do the problems. Do those questions 1 to 6. You've got the answers. You've got the solutions. I'm coming. Okay? Do those problems. Don't play on your phones. Get busy.